Welcome. In this video, we're going to be working a quiz over piecewise defined functions. So we're going to start by just giving a sketch of the graph of y equals f of x on the provided axes. Alright, so when we see y equals x squared plus 1 and y equals x on different domains, okay, we're not just going to draw y equals x squared plus 1 and y equals x and call it a day, right? We're going to have to kind of restrict our view here. And maybe we can draw a little more carefully than that. We know how to sketch the graph of y equals x squared plus 1. It's a parabola that kind of starts at y equals 1. But we're only going to follow that rule when x is less than 0. So there's going to be an open circle here at the place where x is 0, and we would expect y to equal 1. And then it's going to be tough for me to draw. It's the way that this program does not like when I draw right to left for some reason. Okay, but that's a nice parabola there. Okay, that's x squared plus 1 when x is less than 0. And x when x is greater than or equal to 0. Okay, so that would be the line through the origin. Okay, since it's greater than or equal, we'll have a filled in circle, and we know how to draw y equals x. It's a straight line up like that with slope 1. Okay, so that's going to be a good sketch. If they ask, oh no, where am I? Okay, right here. If they ask if g of x is continuous at x equals 2, we're going to check to see, are the two pieces meeting up, right? Are we having a situation like this, and then, the other piece, I don't know, whoops, that was supposed to be a selecting situation here, and now it won't erase. Okay, what's going on here? Okay, the question is, are these two pieces of graph meeting up? Okay, that's what it would be like to be continuous, where the pieces meet up and the circle is filled in, or are they like this? That would be discontinuous. That would be a jump discontinuity that I've got a picture drawn up right there. All right, so we're going to say what happens when I plug in natural log of x minus 1 when I plug in x equals 2. And I'd say natural log of 2 minus 1 equals the natural log of 1. That's the exponent I would put on e to get 1, and that would be 0. And then x minus 2 at the point where x equals 2, that's going to equal 2 minus 2, which is also equal to 0. And this is the reason for my answer, is that both of these pieces equal 0. So I'm going to say yes, g is continuous at x equals 2. Okay. But they could also ask us what value of k makes the function continuous for all x. Okay, so we could have to solve an equation to make this happen. Okay, so if this function is going to be continuous at all x, it's going to be continuous at x equals 1, where I could have a potential jump discontinuity. So I'm going to say I need 4 to the x divided by 2 to be equal to 3x plus 4k at the point where x equals 1. So wherever I see x over here, I'm going to plug in 1, and then I'm going to solve for k, because that'll be the only unknown. So I'll have 4 to the 1 divided by 2 equals 3 times 1 plus 4k. 4 to the 1/2, that's the square root of 4. This is 2, equaling 3 plus 4k. Yeah, I could subtract 3. And divide by 4, and say, all right, k is negative 1/4. All right, the next one was give a piecewise definition of this function that you're seeing the graph of. Right, so I might say this is y equals, I know I said it was piecewise, so I'm looking at the left side, and it looks like a line with slope negative 2. So I'm going to say y equals negative 2x. And, the domain, they're meeting up, so it doesn't really matter. One of them needs to be equal to 0. Maybe I'll say less than or equal to 0. Then on the right, I've got this thing that looks like it's curved, but, not very steep at all. It looks like it could be like a square root or a cube root or a log graph. But if you think about it, 0, 0, 1, 1, 4, 2, that's got to be square root. So this is y equals square root x. And that would be when x is greater than 0. I suppose you could say it's where x is greater than or equal to 0. It wouldn't be untrue. But in general, we try to just have one definition at each x value. And so that would be suitable. But, if you had said x is greater than or equal to 0 and x is less than or equal to 0, we gave you credit. If you had x is less than 0 right there, that was cool too. All the same. All right, now we're going to just sketch a couple of graphs. So f of x is equal to 4 when x is less than 1. Okay, that's y equals 4. That's like a constant graph. Y is always equal to 4 for every x that's less than 1. So just kind of put it like that. And then y equals 5 minus x when x is greater than or equal to 1. Okay, a lot of people graphed this one wrong. I remember when we were grading the quiz, and they kind of like just started at 5 and went down. That's, if you think about it, that's the graph of y equals 6 minus x, because its intercept would be up there at 6. Okay, 5 minus x starts here and goes down, but we're not going to graph it there because that's not, part of the domain. X needs to be greater than or equal to 1. So 5, if I wanted to find like where it starts, I'd plug in x equals 1. And say 5 minus 1 is equal to 4, so it's going to be at the point 1, 4. And then I'm going to go down with slope negative 1. And I think that'll be, that's pretty good. Yeah, that's great. Okay, the next one is y equals 3 to the x when x is not 1, and 2 when x is equal to 1. Okay, 3 to the x, that makes exponential growth. So I need, horizontal asymptotes really close to 0. And then 3 to the 0 is 1. 3 to the first power is 3, and that's, where the graph would be for all x except for right there. So there's going to be a hole in the graph. And, right, we're calling that a removable discontinuity there. And then instead of being at 3 to the first, which is 3, the graph is at 2, so I put a little filled in circle there to indicate that that's where the graph is. And just to remind you about the terminology, this is what we would call a hole in the graph or a removable discontinuity. Alright, form B. So we're going to sketch the graph of y equals f of x on the axes provided. So f of x equals 2 when x is negative. Okay, this one's a lot like the other one. Oh, but it turned out I wasn't really thinking clearly when I made this quiz, I don't think, because I think form B turned out to be quite a bit easier than form A. And, I feel a little bad about that, but at the same time, I've worked really hard to try to make sure they're always, the same difficulty. And I really think this is the first quiz all year that I've made it. There was a significant difference. But 2 minus x, yeah, because there were fewer people going to make that mistake I was just talking about with kind of starting at the wrong place when it starts at 0. 2 minus x is going to start at 2 and have slope negative 1. And okay, that was close, but not it. I'm going to try that one more time. And yeah, that looks good. Okay, that's going to have to be good. All right, and that'll be all. The next one is g of x continuous at x equals 2. Well, at x equals 2, log of x minus 1, okay, that's log base 10, whoa. Log base 10 of x minus 1 is equal to log base 10 of 2 minus 1, which is equal to the log base 10 of 1, and when evaluating that, you're asking to yourself, what exponent do I put on 10 to get 1? And that would be the 0 exponent. Okay, and then I'd say, well, at x equals 2, 2 minus 1 is equal to 1. But, these aren't this. Whoa, whoops. It's supposed to be highlighter. Okay. So since we are not seeing the same value, hold on. Okay, that was better. Since we're not seeing the same values here and there, the function's not continuous. It's got to jump discontinuity. It's jumping from 0 to 1 at x equals 2. So I'm going to say no. G of x is not continuous. But the reason is the work I did up above. Now, if we're asked, what value of k makes this function continuous at all x, we're going to need to take the two pieces of graph, 9 to the x divided by 2, and we need to set them equal to each other. So 9 to the x divided by 2 equals 2x plus 3k at the point where x equals 1. So what we're going to do, we're going to take this 1 and we're going to plug it in wherever we see x. Whoa. And then I'm going to say, all right, 9 to the 1/2 power is equal to 2 times 1 plus 3k. So 9 to the 1/2, the square root of 9 is 3, equals 2 plus 3k. Subtract the 2, divide by 3, and get k is 1/3. And on the back, it's going to ask us to give a piecewise definition of this function. So I'm going to say this is y equals curly bracket, and okay, this looks like a parabola right here. It looks like y equals x squared. So yeah, negative 1, 1, negative 2, 4, that's x squared. And I'm going to say where x is less than 0. Okay, we could say x is less than or equal to 0. It doesn't matter, just as long as one of them has the equals, one of these two pieces. And then on the right side, this looks like y equals x. X is greater than or equal to 0. Okay, but I could have said x squared where x is less than or equal to 0, and x where x is greater than 0. Really, theoretically, I probably could have said both of them less than or equal to and greater than or equal to. It doesn't really matter. Because of the fact that the two pieces of graph met up and then the thing was continuous right here at x equals 0. All right, now with this one, okay, I probably need to shrink this up a little bit. There we go. So if I need to sketch the graphs of these things, yeah, I'm going to just do them both at the same time in the same window. And y is equal to 1, okay, that's right here for all x less than 1. So open circle there. And then square root of x where x is bigger than 1. Okay, I had a really hard time drawing this. Okay, so square root of x would come from the origin and go up, and it would hit 1, 1, because the square root of 1 is 1. So it's going to be a filled in circle, it's going to be continuous. And then it's going to go to the point 4, 2, and it's going to be curved. But, you know, even if you try to put curve on it, it's just, you know, not very curved, because at this point it's x is increasing a lot for each increase in y. And so that's, you know, that's the best sketch I can give. I saw a lot of pretty bad ones on this one, but overall, you know, having the right idea, it was flat and then it grew and it kind of leveled off and the two pieces met up. Okay, so on the right, if I've got y equals 2 to the x for all x except x equals 1, I'm going to just, you know, I think another way to do this, because a lot of y'all are going to be, you know, working this quiz in pencil, that might be a little bit too steep. I'm going to put a couple of points that I'm trying to hit here, 0, 1, and 1, 2, because I know that 2 to the 0 is 1, and 2 to the 1 is equal to 2. And I know that there's a place that's going to be excluded from that rule, but I think it'll be making still a good place to aim at. And I'm going to, you know, kind of act like I have an eraser. Go grab a white pen, or better yet, a small eraser. So I didn't know I had this option, so I'm going to just go in and I'm going to remove that point, because it's a removable discontinuity. So I'm going to put an open circle there, and y is equal to 3 where x equals 1 because of the second rule, and so I'm going to fill in that circle there, and that'll be a really nice sketch. Okay, and, you know, like I said on the other form, a hole in the graph, a discontinuity like that, that's the type of discontinuity we're going to call removable. Okay, so that's all for this quiz, and that'll be all for this video. Thanks for watching.